Welcome to Efiwe, excellence without stress.
Hi guys, welcome back. It's me again, Miss Stella, your favorite physics tutor. And today we're going to take another topic in physics, another very interesting topic. You will enjoy every bit of the topic. Today our topic is measurement of heat energy, and you could be able to apply this to your everyday life. Able to understand it because it's something that we do every day. Measurement of heat energy. We're going to focus on the transfer of heat and how heat is transferred from one body to another. So what is heat energy? Heat energy is that energy that is transferred from a hot object to a cooler one as a result of their temperature difference. The best or the easiest way to explain this is when you want to take your bath in the morning and maybe you felt that, the weather is very cold, and then you boiled water in your kettle, then you poured the hot water into a bucket of cold water. What have you done? You have transferred heat from one body to another. So heat energy is the energy that is transferred from a hot object to a cooler one as a result of their temperature difference. Doing this, you will notice something. The hotter object's temperature will drop because it's now in contact with a colder body, so the temperature will drop, and the cold body will have an increase in temperature. So this transfer of hotness and coldness is what is called heat energy. Heat energy is the energy that is transferred from a hot object to a cooler one as a result of their temperature difference. Such energy always flows from the hot object to the cold object. Heat energy is only one form of energy and is called the thermal energy. Like other forms of energy, it is measured in joules. So our H, which is the heat energy, is what? MC change in theta, where M is the mass of the body, C is the specific heat capacity, because we believe that every material has the amount of heat it can take. It's not just, you can't just pour different heat in different materials. So specific heat capacity is this material, this is its own heat capacity, the amount of heat it can take, and that is why it is specific heat capacity. And theta is the temperature change. Maybe the temperature of the hot body or hot water was 100 degrees Celsius, and the temperature of the water you wanted to pour the hot water in was 37 degrees Celsius. So the change in temperature will be 100 minus 37, and that is what the theta is. So the heat, or the quantity of heat of a particular body, is the mass of the body multiplied by the specific heat capacity and multiplied by the theta change. So where H is the quantity of heat, N is the mass of the body, and theta is the change in its temperature. And the constant known as the specific heat capacity of the body, which is the C. And this constant is dependent on the nature of the body. You should understand that statement. It is dependent on the nature of the body. The type of body will determine the amount of heat it can take. The specific heat capacity of a substance is the quantity of heat required to raise the temperature of a unit mass of the substance by 1 degree Celsius. Don't forget that a unit mass is different from heat capacity. When you're talking about heat capacity is just about the general capacity of a body. But when you say specific heat capacity, it is just one mass of that body. So if the mass of the body is 20, you have to multiply 20 by the specific heat capacity to get the heat capacity of that body. So the specific heat capacity of a substance is the quantity of heat required to raise the temperature of just one of it. So if you want to raise 20, it means you multiply 20 by that specific heat capacity. So it is the temperature required to raise, it is the quantity of heat required to raise the temperature of the unit mass of a substance by 1 degree Celsius or 1 Kelvin. So when H is in joules, N is in what? Kg, and theta is in what? Celsius or Kelvin. You know the unit for temperature is in Celsius or Kelvin. So water has a specific heat capacity of 4,200 joules per kg per Kelvin. Thus, to raise the temperature of 1 kg of water, it is by what? 1 Kelvin. So C, which is your specific heat capacity, is H, which is the heat capacity divided by the mass and divided by the what? Temperature difference. That is the specific heat capacity. H is equals to M multiplied by the change in temperature. The unit of specific heat capacity is joules per kilogram per Kelvin. Then the heat capacity of a body is the quantity of heat required to raise the temperature of the body. So that's the heat capacity. So if it is 10 gram, it is heat capacity. But when I'm talking about 1 gram of a particular body, I'm talking about the specific heat capacity. But the heat capacity of a body is the quantity of heat required to raise the temperature of the body by 1 Kelvin. So the unit of heat capacity is joules per Kelvin. Is joules. That is because it is E divided by what? The temperature change. So heat capacity is mass multiplied by the word specific heat capacity. Heat capacity is the mass multiplied by the specific heat capacity. So H is equals to MC theta, and recall that MC itself is the word heat capacity. MC is heat capacity, so that is heat capacity multiplied by the theta will give us our what? Our H, which is the heat. So where Cp is the what? Thermal capacity or the heat capacity. So quantity of heat is equals to thermal capacity multiplied by the temperature rise. So the quantity of heat itself is the heat capacity multiplied by the rise in temperature. So we have a question here. A copper rod was with heat capacity of 585 joules per Kelvin. So this is the heat capacity. The amount of heat that body can take is what? 585 joules per Kelvin. So that's heat capacity. It's heated until its temperature changes from 35 degrees Celsius to 80 degrees Celsius. So calculate the quantity of heat supplied to the rod if the specific heat capacity of copper is what? 390 joules per kg per Kelvin. Then find the mass of the rod. Find the mass of the rod. So we have it that we know that heat, quantity of heat, is heat capacity multiplied by the change in temperature. We've already established that quantity of heat is the heat capacity multiplied by the temperature rise, and we have that our heat capacity is what? 585 joules per Kelvin. Then the change in temperature is what? 80 minus 35, which is going to give us 45, and when you multiply it, you are going to get this. Changing this to kilojoules, we are going to have to divide it by 1000, and we have 26.33 kilojoules. 26.33. So that's the quantity of heat. That's the quantity of heat. The quantity of heat is heat capacity multiplied by the temperature rise. So we are now asked for the mass. We remember the relationship is specific heat capacity is equals to mass times heat capacity is equals to mass times specific heat capacity. So we have the heat capacity and we have the specific heat capacity. Definitely we can get the mass of the body. So the mass of the body is just the heat capacity divided by the specific heat capacity, and that was 1.5 kg. 1.5 kg. So specific heat capacity by method of mixtures. By method of mixtures, what does this mean? Mixture, maybe you boil water and you put a block inside. The hot water is going to convert its heat to, is going to send its heat to this hot block, and this hot block can be used to transfer temperature to another body. So method of mixture, it can either be block and water, it can either be water and water, like the one that I explained initially, that you wanted to use water from your kettle to warm up your cold water, and that is method of mixture. And we have the one that is without the method of mixture, just by heating a block in fire, like this picture we are seeing. You can see this block that is placed in a Bunsen burner and is heated. Let's read it. The calorimeter is an apparatus used in experiments that involve the exchange of heat between the two bodies at different temperature. That is a calorimeter. The apparatus is usually made of copper or aluminium, which are good conductors of heat. The most common method employed in calorimeter experiments is known as the method of mixtures. Yes, the method of mixture. This one here is not the method of mixture. What this is used to do is just that we heat the stone, or we heat the metal. You can put it on the gas or anywhere, and after heating it, you transfer it into either water gently, and then it's going to transfer its temperature to the water. It's going to increase the temperature of that water. So what are the things you need to know to be able to determine, okay, this thing has actually changed the temperature of the water? First, you have to know the mass of this block. Yes, you have to know the mass of the block, because if you know the mass of the block, you'll be able to know the mass when it's inside the water. You'll be able to know the mass when it's inside the water. You have to know the mass of the water. You have to know the temperature of the water you are sending it to. You have to know the initial temperature of the water and the final temperature. Okay, I brought something that is very hot and I put it inside this liquid. This liquid was 10 degrees Celsius initially, but when I now put this block inside, what happened? It increased the temperature to 20 degrees Celsius. Definitely, the change in temperature is what? Change in temperature is now the theta final temperature minus the initial temperature. This particular block too has its own temperature, and that's how you're going to be able to know the temperature that it's brought into the water. So this one is now the method of mixture. The method of mixture is this block, we're going to put it inside a bucket of water, then we're going to boil both of them together. The water will boil and this block too will block. So after the water has reached 100 degrees Celsius, that is the boiling point, you will quickly transfer it into another liquid. The liquid will be inside a calorimeter, and that calorimeter is a good conductor. You quickly transfer it, but before you transfer it, you must have registered the temperature of the water in the calorimeter, else you will not know the difference. You have to know that, okay, before we put this block inside, though, this water was this temperature. Now that we are putting this block, this is the temperature, and that is all what its capacity is all about. I mean, that's what a measurement of it is all about. The transfer of it. Something was cold, we made it hot. Something was ice, it's now water. What difference? What happened during that period? So that is what we are trying to explain in this class. So the apparatus is usually made of copper or aluminium, which are good conductors of it. The most common method employed in calorimeter experiment is known as the method of mixture. In this method, a hot substance is mixed with a cold substance, during which heat flows from the hot to the cold substance until both reach the same temperature. Yes, there is always a stirrer. After you've transferred the hot object into the normal or cold object, then you have to stir. Then it will get to a time when the temperature will not increase again, because you know the thermometer, once you put the thermometer, if the temperature is still high, the thermometer will continue to move, but it will get to a time that the thermometer will just stop. Then that tells us that, oh, it is at equilibrium point. This is the temperature is already at equilibrium. So when this happens, it follows that the quantity of heat lost by the hot substance must be equal to the quantity of heat gained by the cold substance. You know, we already have this law. Energy can neither be created nor destroyed, but must be converted from one form to another. So the same thing, heat lost must be equal to heat gain. So if the metal is the solid is losing its heat, definitely the liquid must be gaining that heat. That is just what this means. Heat loss must be equal to what? Heat gain. So this is the principle of mixtures, which is applicable in all problems involving a heat transfer. This assumes that no heat is lost to the surrounding. Losses are, however, often possible through the process of conduction, convection, radiation, and evaporation. To reduce losses due to conduction, the calorimeter is surrounded with a poor conductor, e.g. cotton wool or any other thing. Then this is called lagging the calorimeter. Losses due to convection and evaporations are reduced by providing the calorimeter with a lid containing holes to take thermometer and a stirrer. Yes, the calorimeter will be covered. Then there should be a stirrer so that we can be able to stir it and get the equilibrium temperature. Experiment to determine specific heat capacity of a solid by method of mixture. That's what I've been trying to explain. Look at this metal here. Now there is a rope to use to pick it. We tied this rope, then we boiled it with the water. That's mixture. Mixture is different from when you are just eating the solid alone, but this is method of mixture. The liquid and the water were boiled together, and when the water boiled at 100 degrees Celsius, we quickly did what? Took it and transferred it here. We transferred it to this point. Okay, yes, okay, it was here. This is the point of boiling. So what happened? We quickly transferred it. You see that this is the calorimeter. The calorimeter is covered and there is a stirrer. And what's the stirrer used for? To get the equilibrium temperature. Then we have the thermometer. So the solid in the form of a brass or copper, this is it. Block is weighed. You have to know the mass. Tied to a string and left for some minutes in a beaker of boiling water. You know that we are looking for heat, and heat is MC change in theta. Heat is what we are looking for. We want to look for heat loss is equals to heat gain. So heat is MC change in theta. Then you have to know the mass. You have to know the specific heat capacity, and you have to know the change in temperature. That is just what it's trying to say. So look at it now. Let's go to our board and try to just visualize what is happening. So this is our board now. We have, this is a container, this is the candle that is like the heat provider. Then we have the brass inside it, and there's water here being boiled, right? Then what do you want to do? You want to use this to warm up or to increase the temperature of this water inside this calorimeter. The calorimeter is covered, there is thermometer inside, there is stirrer inside. What are the things we need to know? Yes, first thing, I need to know the mass, because I'm looking for heat lost equals to heat gain, right? Is equals to heat gain. So what are the things I need to know? One, I have to know the mass, because heat is just MC change in theta, right? And MC change in theta, which one is losing, which one is gaining? This one is losing, this one we lose is it, this one we gain. But I have to know the mass. So I have to know the mass of that stone, right? Yes, I have to know the specific capacity of the stone, and I have to know the change in temperature. Yes, the initial temperature of this stone, I have to know it. Of the water, we have to know it. Then we have to know the final temperature when it came to this place. Because if you don't know the change in temperature, you won't be able to know the temperature, right? For this one too, there are two things here: the water, calorimeter, and the water. How can I know the mass of the water? By measuring the calorimeter when it is empty first. Then you now pour water inside, then you measure the calorimeter and plus water. So if I say calorimeter is 10 gram, then calorimeter plus water, it became 30 gram. What is water? Water definitely is 30 minus 10. So the mass of water is just 20 gram. It's just as simple as that, because those are the things losing it. The things losing it here now, the one losing it is here, the one getting it is here. So those are the things. If you understand that simple principle, you'll be able to solve any question on it. So the calorimeter, say the solid in form of a brass or copper block is weighed and tied to a string and left for some minutes in a beaker of boiling water. Yes, look at it now, left there. The calorimeter together with the stirrer is first weighed. The calorimeter without anything, you have to wait, so that when you put water, because you cannot pour water on a scale now, you can't know the mass of water, because it has to be in a container for you to measure water. It's not something that, okay, it's a block. If it's a block, I can measure block, but water must be. So the first thing is you have to measure the calorimeter empty. Then you now pour the water inside the calorimeter, then you now measure it. So then, for me to now know the mass of, okay, this is the mass of the water, is now to remove the mass of the calorimeter from the mass of calorimeter plus water. You will know the mass of your water. So the initial temperature of the water is read with the thermometer. Yes, the initial temperature is read. After the solid has stayed in the boiling water for about 15 minutes, it is quickly transferred into the water in the calorimeter. The calorimeter is covered with the lid, and the water is gently stirred to ensure a uniform distribution of temperature. The highest steady temperature of the mixture is read and recorded. So let's check what we have. So mass of the solid now is M1. The solid that we want to eat is M1. This one I want to transfer it to us is M1. Mass of the calorimeter plus stirrer is that is serving as the mass of the calorimeter when the calorimeter is empty. So mass of calorimeter plus stirrer is equals to the M2, right? So what is, okay, now mass of calorimeter plus stirrer plus water is equals to M3. What is now the mass of the water? The mass of the water is M3 minus what? M2. As simple as that. So initial temperature of the water plus calorimeter is what? 0 is theta. Final temperature of the mixture is what? Final temperature of the mixture will be what? Will be the initial temperature. Don't forget that their own final temperature now will be lesser. So it will be the new temperature minus the initial temperature. So temperature of the boiling water is 100 degrees Celsius. Specific heat capacity is C, and specific heat capacity of water is what? 4,200 joules kg. So let the specific heat capacity of the calorimeter material be C2. So heat loss is equals to heat gain. So M1C1 minus theta 100 minus theta 2. Why is it like this? Let me explain this to you. This is the solid, the mass. This is the specific capacity of the solid. The temperature of the solid is 100 because we boiled the water to be 100 degrees Celsius minus theta 2. That theta 2 is the temperature that is going to gain when it enters into the liquid. Then its gain. What are gaining it? The thing gaining it is the water. That's why we have M3 minus M2. That was what I was trying to explain to us now. M3 minus M2 times 4,200, then theta 2 minus theta 1. This one is the mass of the what? Of the calorimeter. It's the mass of the water inside the calorimeter. But we cannot measure water alone. Why? Because the water cannot stay on the measuring on the mass this thing alone. So that's why we have to subtract it from this and get this. So neglecting heat losses to the surrounding, heat loss by solid is equals to heat gain by water plus heat gain by the calorimeter and stirrer, and we'll get our answer. So that's all. Let's go to our board and try to just visualize what we just said. So look at it now. We've already agreed that, okay, this is the solid, Abi. Let's say mass of the solid is equals to what? M. Let's assume it is M1. The solid is the temperature of water, boiling water. We know the temperature of boiling water is what? 100 degrees Celsius, right? And I said something again. You have to measure the calorimeter and the stirrer first. Let's assume that one is M2. Then you have to measure calorimeter plus stirrer plus water. That will give me M3. So now if I ask now that what is now the mass of water? The mass of water that we are transferring the stone is the mass of water will be the M3 minus what? M2, right? So for calorimeter we have M2. So heat loss is equals to what? Heat gain. Heat loss is equals to what? Heat gain. And don't forget the formula of heat. Heat is MC change in theta is equals to two things are gaining heat here. The water, MC change in theta for the water. This one is for the water plus MC change in theta for the what? For the calorimeter. Those are two things gaining heat. So this one now mass. Let's assume that C of solid is for the solid. C of calorimeter, this is for the calorimeter, then C of water is for the water. So M is what? M1, right? Multiplied by C of solid, right? The change in temperature will now be theta 2 because change in temperature is 100 because the water was boiled, but we don't know the new temperature. The new temperature will be the temperature when it enters water. This was it before now. When the solid was there, 100 degrees Celsius. But when it now entered this new calorimeter, we don't know the temperature. That was the theta that we are now what? Looking for. So minus theta final, that's the one that is losing it, is equals to the ones that are now getting it. Mass of the calorimeter plus stirrer, that's M2, right? The change in theta now will now be what? Theta final minus their own theta 1, because theta final is bigger, but this one's own first theta is bigger than his own final. But these people's own, the new theta that is coming is bigger than their initial theta. So plus the one for okay multiplied by the C of what? The calorimeter plus the mass of water. Abi, what's the mass of water? That's M3, right? Multiplied by the C of water multiplied by the change in temperature. The change in temperature is the same, which is T final minus theta 1, and that is how to get heat loss is equals to what? Heat gain. And that's just the principle behind every order of it. So we've done that. So let the liquid of unknown specific capacity, this one now is water and water. This is water and water. Let the liquid of unknown specific heat capacity instead of water, the calorimeter with a solid whose specific capacity is known. So this is experiment to determine the specific heat capacity of liquid by method of mixture. So we want to know the specific heat capacity by method of mixture. The liquid of unknown specific capacity instead of water in the calorimeter with a solid whose specific capacity is known. So the specific heat capacity of the liquid is calculated as below. You know the specific heat capacity of solid, of the calorimeter, and of the liquid. This is just what we've explained. Mass of solid is M1, mass of calorimeter is M2, mass of stirrer plus liquid is M2. So mass of liquid will now be M3 minus M2. We've explained that. That was what I was explaining. So the initial temperature of the calorimeter, which you must know is theta 1. The temperature of solid in boiling water, 100 degrees Celsius, and this is what I just explained on that board, and we can get anything we want to get here. We can get anything we want to get. Let's check this example. The hot water tap of a bath, just think about it. I already explained to us that when we want to have our bath and the water is cold. You want to mix it with what? With cold water. So a hot water bath delivers water at 85 degrees Celsius at a rate of 8 kg in a minute. The cold water tap of the bath delivers water at 30 degrees Celsius at the rate of 20 kg per minute. So this is just two things, hot water and cold water. You know, basically you are going to need more cold water than more hot water. So the hot water is giving 8 kg per minute. The cold water tap is giving what? 20 kg per minute. If both taps are left for 5 minutes, calculate the final temperature of the water bath, ignoring heat losses to the surroundings. So simple, right? Let the final temperature be theta degrees Celsius because we don't know the mixture. Yes, the final temperature now is going to be initial minus the final, right? Because hot water is having 85, cold water 30. When I subtract it, I will have my final temperature. So mass of hot water delivered in mass in 5 minutes is 8 times 5, because it was delivering 8 kg per minute. That's 8 times 5, 40 kg. Mass of cold water liquid delivered in 5 minutes also. This is hot water bucket, this is cold water. For 5 minutes it gave us 40 kg because it's 8 times 5. The hot water too, 20 times 5. No, the cold water 20 times 5, 100 kg. You know the cold water must be more than the hot water. What is the change in temperature? The change in temperature is just 85 minus what? The final temperature that we do not know. So heat lost by the hot water in cooling from 85 degrees to theta is 40 times C times 85. That's heat lost by the hot water. The hot water's mass was 40. The specific capacity of water we do not, specific capacity of water we were given, yes, and the change in temperature, the water was 85 initially minus the temperature is to be when it enters the cold water. That's for the heat loss, that's the one that is losing heat. So where C is the specific capacity of water, the heat gained by the cold water. The cold water now is going to be raising from 30 to theta. So theta is more than the initial temperature of the cold water. So that's why we have mass of the cold water multiplied by C multiplied by theta minus 30 degrees Celsius. So C we cancel C. That's just what this one is just going to tell us. So 100 multiplied by theta minus 30 is equals to this, and we get our theta. We get our theta. This is another question. I hope you understood that very clearly. It's so simple actually. So an electric heater rated 15 volts and 40 watts fitted into a metal block supplies heat. This one now is heating the metal with electric. This is by electric method. Supplies it to the block of mass 1.5 kg, and this was the specific capacity. Calculate the temperature rise. Don't forget, this is now this one that we are using power. We are using electricity. So power is 1 IV. That is the current multiplied by voltage, and that was equals to 40 watts. So 10 minutes is equals to power times time. You have to convert your time to second, and that was 40 times 10 times 60. So we got our what? Our power in joules per second. So that's the power. So the temperature rise is theta K, because look at it now. An electric heater rated is fitted into a metal block. It was that electric heater that is going to be losing it to the metal block. Right? So heat gained by the metal block is the mass of the metal block. Heat is MC change in theta. Specific heat capacity of the metal block, then the change in temperature that we do not know. Why the one that is losing heat also is his own mass multiplied by his own specific capacity. It also has specific, it's just his power. Power is equals to the change in temperature. So heat produced by electric heater, because the heater is just producing it, and that was 2400. The heat is just IV. Then you are going to equate it to MC change in theta, and we are going to get our theta. So this is just it. This is a heater. This is a block, and inside this block there is a space that we can put an electric heater. So this is an electric heater inside now. This is the wire of the electric heater. Wire of electric heater is connected to a socket. This is the socket on the wall. So it was heated, and don't forget, this one is electricity. So power, as we know, is IV. So it's this IV that is losing current to this block. This block will now be MC change in theta. So what is my I? What is my V? And that was what we tried to get here. Oh, sorry. So this is it now. This is the block. This is the block here. This is the block. This block is connected to an electric heater. This heater is used to warm up this what's it called, this block. It's not like when I put it inside liquid, you know, that one is method of mixture, but this one, there is a hole, and we are now sending we are sending heat to this metal using the electric heater. So P is the power, that is the one that is producing it. So heat produced is equals to heat gained in this situation. So that's P is equals to IV is equals to MC change in theta. This is the mass of the solid. This is the specific heat capacity of it, and the change in temperature, that is theta 2 from minus theta 1. So let's go back. So we have it now. They said an electric heater rated 15 volts and 40 watts. So you know that this is telling us what? That 15 volts and 40 watts. How can I get my IV? So IV is what? 40 watts. That's what it's trying to tell us. Power is in watts. So we have 40. And in how many minutes? They told us in 10 minutes. So we have to change it. So 40 times 60 will give us what? Our IV. Because IV is 40. Then 40 is just 10 times 60. Our power is 40. How many minutes did it work for? It worked for 10 times 60 because we have to convert it to seconds. And we got our power as 24,000 joules. So 24,000 joules now. Because P is equals to IV, right? But we've been given, because anytime you see watt, it is the power. They give us as 40 watts. So this 40 watts worked for how many? They said it worked for 10 minutes. Abi, is it 10 minutes? Yes, it worked for 10. So we have to convert it to seconds. That's why we have 40 times 10 times what? 60. And that was where we have our 240. This is where we have this one. So this one now is equals to the mass. What's the mass of the metal? The mass of the metal is 51.5 kg. What's the specific capacity of the metal? Of the block, 460. Then we don't know the change in temperature, right? So it will be all of this. It will just be theta is equals to 24 divided by 1.5 times 400, and we're going to get our theta. We're going to get our theta as 34.78 Kelvin or degrees Celsius. So change of state, latent heat. So this one is just so different. You know the one we've been talking about. There is always a rise in temperature. Temperature will move from one state to another. All the ones we'll be talking about. The temperature has always been rising. Maybe, okay, for example now, maybe the temperature was 30 degrees. When you now pour hot water, what will happen to the temperature? It will increase to 50. But when you talk of latent heat of fusion, it's that moment at 0 degrees Celsius. It happens in 2 points, at 0 degrees Celsius and at 100 degrees Celsius for a while. There is no change in temperature. Change in temperature is 0. There is no change in temperature, and that's latent heat of fusion. So matter can exist in 3 states. We have the solid, the liquid, and gas. Supply of heat to a solid will not only cause the change in temperature to rise, but can also cause the solid to change to a liquid in a process known as fusion. Similarly, a liquid can change to gas or vapor through the addition of heat by the process of vaporization or evaporation. So look at it now. This is this moment now. What happened? Heat is increasing, temperature is increasing. I mean, that's the solid. But when ice at this point of 0 degrees Celsius, when the ice is melting, the temperature does not change. After this point again, there is another increase in temperature. When it gets to 100 degrees Celsius again, there is a moment whereby the temperature is constant. So the reverse process are also possible. Removal of heat from gas can cause it to revert to a liquid, and removal of heat from a liquid can cause it to revert to solid. That's just conversion. Latent heat is the heat supplied. This is it. It's the heat supplied or removed, which causes a change of state. That is, this thing it moved from ice, that's 0 degrees Celsius, to water, but there was no change in temperature. You can see that the temperature here is constant. You can see it from here. The temperature here is constant. It moved from ice to water at this point, and there was only what? Phase change. So this kind of phase change occurs in 2 places, at 0 degrees Celsius and at 100 degrees Celsius. There will be a change. This one now is going to change from water to vapor, and there was no change in temperature, and that is what is called. So latent heat is an invisible heat, hence the thermometer does not dictate it. It depends on the mass and nature of a substance. The latent heat of fusion. Latent heat of fusion is the quantity of heat required to convert a substance from a solid to its liquid state without a change in temperature. It's different from the ones we have been doing. All the ones we've been doing, there was a change in temperature. When you took you poured hot water into cold water, what happened? A change in temperature occurs. But this one is the quantity of heat required to convert a substance. That's just for change of state without a change in temperature. When only unit mass of the substance is considered, the heat involved is known as specific latent heat. We've explained this. Specific, just the mass. Specific latent heat. When only the unit mass of the substance, that's for one, we call it specific latent heat. So specific latent heat of fusion of a substance is the quantity of heat required to convert unit mass of the solid at the melting point to its liquid form without a change of temperature. So in SI unit, specific latent heat of fusion is expressed in joules per kilogram. So the heat involves the mass M, and the specific latent heat of fusion is given as H is equals to ml. You can see there is no change in temperature. The quantity of heat in specific capacity is H equals to ml change in theta. But as I showed you in the previous slide, there is no change in temperature in this one. There is no change. There is only a phase change from ice to water, from water to gas. A phase change, but no change in temperature. So that is what this is talking. And this is a question. A copper calorimeter weighing 40 grams contains 200 grams of water. So let's look at it. It contains 200 grams of water. We have the copper calorimeter. It contains 20 grams of water at 35 degrees Celsius. So this is it now. Let's go to our board. So this is the copper calorimeter now. This is it. It contains 200 grams of water. We can change it to kilogram. 200 grams of water, right? Then they now put ice inside. You know that the mass has changed. Now the mass will be addition. So they put mass of 20 grams inside the calorimeter. Let's read the question again. Let's read it again. Let's read it again. Sorry, the mouse is not doing what it's supposed to do. Okay, so look at it now. So they said a copper calorimeter weighing 40 grams. So this is the copper calorimeter. Let's assume this is it. It was weighing 40 grams. Okay, contains 200 grams of water. Okay, sorry, the copper calorimeter was 40 grams, but it contains 200 grams of water at 35 degrees Celsius. So we have the initial temperature, right? We now put 20 grams of dry ice inside it. You know that dry ice we do what? We actually become what? We actually become water. But what will happen to this, what is it called? The water itself. The water is going to lose it. Because yes, the temperature was 30. When you add cold water, when you add ice to a water that is maybe 35, the temperature will drop. So a copper calorimeter weighing 40 grams. This is a copper calorimeter. They now added 200 grams of water to it. At 35, they now put 20 grams of ice is added to the water. And this reduces the temperature to 35 degrees Celsius. You should understand that. This reduces the temperature to 35 degrees Celsius after all the ice has melted. What value of specific latent heat of fusion of ice is given by this experiment? Sorry, this one should be 25 degrees Celsius, not 35. That was a typo. 25. So specific latent heat of water is, specific capacity of water is this. Specific heat capacity of copper is this. So some things are happening. Things are happening. The water is going to drop in temperature. It's going to lose. But this other one is not changing temperature. It's only changing state. So let specific capacity of fusion be L, because we don't know it. Mass of copper is 40. We change it to kilogram. Mass of water, we change it to kilogram. Mass of ice added, we change it there. Heat gained by ice in melting, yes, is ml, because it's only phase change, but the temperature is not rising. So heat required to raise temperature of melted ice from 0 to 25 is the mass, specific capacity of water, multiplied by the change in temperature, because its temperature became 25, something that was 0 degrees Celsius. You know water, ice is 0, and it became 25. So this is it. So the total heat gained now is the one for phase change plus the one for it to what, to change its temperature, because its temperature will change from this point to this point. So but heat lost by water, the water is going to lose heat, because ideally the water was 35 but it became 25, so it's 0.2 times this times, and give us this. Also the calorimeter too is going to lose, and it's just the same process. So heat loss is equals to heat gain, and when we add our answers together, we are going to get the latent heat of this thing, and it's 3.2. Because the question say what is specific latent heat of fusion of ice? It is 3.23 times 10⁵. So this is so easy. I've explained to you. What happened is this: there is a calorimeter, it contains water, and the calorimeter itself is 40 grams. The water is 200 grams. We now put ice inside. The ice is going to reduce the temperature of the water, but what's it called? The ice changing from ice to water, there is no change in temperature. Are you getting that? But the ice moving from 0 to 25 degrees Celsius, you have to calculate it also. But the phase, the latent heat of fusion, is that moment where the mass is changing from the ice is changing from ice to water without a change in temperature, and that was what we did. So heat loss is equals to heat gain, and we got this. So the latent heat of vaporization is the process in which a substance changes from liquid to gaseous state. So specific latent heat of vaporization of a substance is the quantity of heat required to change unit mass of a substance from its liquid at boiling point to vapor without a change in temperature. I've explained this in the last question, and it's just the same process too as the latent heat of fusion, but H is also equals to what? ml. Thank you. See you in our next class.